My name is Yiltan, and I am presenting the paper that I worked with my colleagues at the Parallel Processing Research Lab. It's efficient multipath NVLink PCIe UCX-based collective communication for deep learning. So the outline of my presentation, I am going to introduce some background information such as OpenMPI UCX, and then what motivated us to do this work. And then we'll go over our proposed designs. In this paper, we had two parts, our multipath copy design, and then a collective communication design, which is our multipath copy used in the context of a collective. Then we will move on to our results, where I looked at the microbenchmark layer and then the application layer. And finally, I will conclude our work and what we plan to do in the future. So HPC is solve large complex problems in many domains. And on these HPC clusters, communication is one of the major bottlenecks. And as the popularity of heterogeneous systems grow, making sure that communication is optimized for accelerators such as GPU is incredibly important for the new workloads that we see. So MPI, that is one of the most popular parallel programming models that is used on HPC clusters. And MPI provides a few different communication APIs, point-to-point, partitioned point-to-point, RMA, and collective communication. And as the previous speaker said, we've seen a large growth in deep learning in recent years, and especially on HPC systems. And these HPC systems use the aggregate power to solve complex deep learning tasks. So let's go a little bit deeper into deep learning, MPI-based deep learning. So one of the most popular frameworks for distributed deep learning is Horrorwood. And Horrorwood is compatible with a few different deep learning frameworks such as TensorFlow, PyTorch, and MXNet. So the models would be implemented with those frameworks, and then Horrorwood ties it all together and is used as a distributed trainer. So on the right-hand side, we can see a figure, and I profiled the MPI or reduced usage in a few different models. And we can see anywhere from 17 to 83% of application runtime is spent in MPI or reduce. And up to 80% of runtime is spent just in the GPU-based MPI or reduce. So we can see MPI communication is a major bottleneck in these applications, and specifically MPI or reduce with GPU buffers. So let's give a bit more background into OpenMPI and UCX. So UCX provides an abstract communication primitive to best utilize hardware. So it allows data transfer between different regions on GPUs using 2.IPC or GDR copy and so forth. And point-to-points in UCX are implemented within their put-get operations within their library. And then we use OpenMPI for our distributed training. And MPI is an open source MPI implementation. And the point-to-point layer of OpenMPI, we configured it to use UCX, and it uses UCX directly. And then within OpenMPI, the collectives use those point-to-points, which ultimately rely on UCX. So what is our research goal? We want to improve the performance of deep learning applications. And specifically, we want to enhance point-to-point communication and collectives for MPI's large messages on GPUs. So the motivation for this work, currently data transfers between two GPUs send the data directly between two devices. So if we look at a diagram, the solid red line at the bottom, UCX sends data directly from GPU 0 to GPU 1 using a zero copy put operation. And this results in the 6 NVLinks connected to the host to be idle during this operation. So that's a lot of unused potential bandwidth that we could probably use. So we asked ourselves the question, can we design a mechanism that uses all of these paths? So we did some preliminary investigation, in the blue line, you can see the default mechanism used by UCX. And then in the colored lines, you can see just using a host stage copy. And we varied the number of streams that we use for that host stage copy. And we saw that stream count impacts the peak bandwidth when using that host channel. And then the stream count is dependent on the message size. And we saw up to 53 gigabytes of unused bandwidth. So there is good potential for our design, for a multipath design. Using the host channel alone does not really improve. It's actually worse than using the direct, but we wanted to see if we could combine both and gain something from that. So this is an outline of our algorithm. So initially, before we initiate the copy between the two devices, we tune the copy parameters. So we calculate how much do we send directly to the adjacent GPU and how much we send via the host. Because we saw the bandwidth that's available to us in those two channels is not exactly the same. So we have to distribute it in an appropriate manner. And we also further subdivide the data that we are sending through the host, which I'll discuss a little bit more in a second. So the first step after we've done our parameters is to initiate the parallel copy. And that has two parts. First, we copy the data from GPU to GPU, and this is exactly how UCX works by default. We change this by, instead of sending the entire buffer, we only send the portion of the buffer. And then we add our code which deals with the host stage copies. So it's fairly simple. We copy from the device to the host and then back to the device. But we split that buffer that's going through the host and place each partition of that buffer on a separate stream. And this allows us to pipeline that copy and get a little bit more performance out of it. So once we designed that multipath copy, we wanted to use it in a collective because, as we saw earlier on, deep learning relies heavily on MPI or reduce. So we went about designing this collective, and the first step is the intra-socket multipath reduce. So this is using the mechanism just to transfer the data to the adjacent GPU. And then we exchange the data between the leaders on each socket. And then finally, we broadcast the data back. So the algorithm itself, it worked, but we did some additional design optimizations to make it more performant and comparable to other MPI implementations. So we pipelined steps 1, 2, and 3. And the main reason for that was that the step 2 was quite slow. And that's because we are limited by the XBus bandwidth. So one thing we did, we switched between NVLink and PCIe when transferring between the sockets, because we can take two paths. We can go PCIe, XBus, and then PCIe back, or NVLink, PCIe, and NVLink back. But as XBus is the limitation when transferring between the two sockets and not NVLink or PCIe, switching between the two doesn't really impact the performance in terms of micro benchmarks, but we'll explain why we did that in a second. And then another thing we did is we noticed using our multipath copy, sometimes there'll be some congestion. So we disabled it when appropriate and just use the direct peer-to-peer copy. So yeah, so the reason we did this two dynamic switching was to minimize intra-socket congestion and to also alleviate some of the issues with inter-socket congestion. So we use the systems at the University of Toronto at SciNet, and these are IBM Power 9 systems with 4 V100 GPUs. And this is the software setup we use. We use OpenMPI and UCX, and then we compared it to a few different other MPI implementations and Nickel. And then finally, we evaluated it with Horwood and TensorFlow. So first off, let's start with the micro benchmarks. We implemented our multipath copy in UCX. So we see when we used our multipath copy, we saw a 1.67 times speed up compared to UCX's default implementation. We noticed we only saw performance for the larger messages. For the smaller messages, using this multipath copy, it wasn't beneficial. But as deep learning uses large messages, we saw this to be promising. And then for MPI unidirectional bandwidth, we got 1.84 times speed up. And you can see we beat every single other MPI implementation. And the reason is those other MPI implementations only use that single path when transferring between GPUs on the same socket. So now that we've evaluated a design at the point-to-point layer, let's move up to the collective layer. So we are going to go with these message sizes from 512 to 4M. And we can see 2.75 times speed up over OpenMPI plus UCX at 1 megabyte. And then we see 2.03 times speed up over Spectrum MPI. We suspect that Spectrum MPI uses a host staged copy, as we know that OpenMPI does, and the performance is fairly similar. So that's why we see those blue and orange bars to be significantly higher. And at this message range, we see comparable performance to OpenMPI using HPCX. And then for the message range of 8 meg to 64 meg, we saw comparable performance to optimized libraries at 8 megabytes. And at 16 megabytes is where we started to see our design perform a little bit better. So at 16 megabytes, we see 1.09 times speed up compared to HPCX, and 1.26 times speed up compared to NVLink GDR, and 1.25 compared to nickel. And then for large messages, we got significantly lower latency than the HPCX implementation. And at 1 gigabyte, we see a speed up of 1.47 times over NVLink GDR and 1.38 over nickel. So these message sizes is where we see the most benefit of using our multipath copy with our collective design. So finally, we evaluated our results on some applications to see how they fit. So we tried with a few different deep learning models, and this was just using the synthetic benchmarks for Horwood using TensorFlow. So for ResNet 50, we see a 1.56 speed up. And then we tuned the parameter Horwood fusion threshold because we noticed by varying this value, we could increase the performance that we saw. So you can see from increasing from 64 megabytes to 128 megabytes, we got a little bit extra in our throughput results. And we can see how the message sizes changed, increased the message sizes as we played with this value. So we noticed the correlation between this Horwood framework tuning value and MPI or reduce message sizes. So then we tried it with ResNet 152, and we got a 1.40 times speed up. And with this model, we modified the fusion threshold from the same way as we previously did. But we didn't really see too much performance improvements. We saw from 64 megabyte to 128 improve, but past that, it was fairly stable. And we can see how this affected the message sizes as we tuned it. Sorry, I missed the point. And we noticed that when we increased the buffer size with this model, it also increased the smaller message sizes that were present. And then for DenseNet, we saw a 1.26 times speed up. But when we modified the fusion threshold for this model, it seemed fairly unresponsive. We can see the message sizes didn't really change, and the actual application results did not change. So yeah, had minimal impact. And finally, BGG16. For BGG16, we saw a 3.42 times speed up. And we saw the biggest speed up for the larger message sizes here. And with this model, playing around with the fusion threshold, we were able to increase it. And this model was very responsive to this parameter. So in conclusion, deep learning workloads use MPI or reduced collectives extensively. And there's a great importance on large messages. Intranode MPI or reduced communication in MPI is not well optimized. Well, the open source versions anyway. We proposed intra-socket multipath point-to-point communication in UCX, and we now utilize that unused bandwidth. And this directly improves MPI point-to-point without any additional modifications to OpenMPI. And then finally, we proposed a new hierarchical MPI or reduced collective design. And this design is NVLink PCIe aware. It now uses a GPU reduction, and it uses our multipath copy design. For deep learning applications, we see up to 3.42 times speed up with these proposed ideas. For our future work, we intend to study GPU-based HPC and other deep learning applications, because what we studied was synthetic benchmarks and it was limited to Horwood. So we'd like to see what else we could do. And we'd also like to apply the multipath copy to other hardware topologies. In this work, we only looked at these IBM systems with NVLinks to the host. We didn't look at other systems that have a mixture of NVLink and PCIe connecting the GPUs. And then finally, we plan to devise a cluster-wide algorithm that extends our single node algorithm to multiple nodes. And finally, we would like to study dynamic tuning approaches. So in our design, there was lots of static tuning to get the optimal bandwidth for the point-to-point or the collectives. So thank you. I would like to take any questions.
Hey, thank you, Ritan, for a good presentation. There are 2 questions in the Slack channel currently. So first one is, have you considered using multiple methods with small message, large message thresholds to get the best of both worlds with single or multipath?
You consider small message and thresholds as opposed to a single? Yes. So I didn't show it in the put results because I wanted to show where we see the performance improvement. But once we moved on to our MPI or reduced design, I had a simple if statement to use the single channel to a certain threshold and then moved on to the multipath design when appropriate.
I see. Okay. The second question in the channel is, from the UCX perspective, our goal is to support collectives via UCC, an open source collective library that leverages UCX. We leverage UCX, Nickel, and Sharp in future as a transport. Have you guys looked at UCC? If so, what do you think? How you can integrate into something like UCC?
Yeah, that was actually one of the comments we got during the peer review process. So we intended to compare our implementation to that collective library and see what happens. But as for works of implementation in that specific library, we haven't really looked at that at this point in time.
Okay, thank you. One other question I had in your design optimizations, where you were talking about dynamically switching between PCIe Express to PCIe and NVLink Express to NVLink. So you said that you guys observed it based on certain message sizes, you observed it, and then you dynamically switch it in the algorithm. Now, how is it fed into the algorithm? Is it something that is provided like a statically, or is it something that's determined inside the algorithm?
Mm-hmm. So although it switches dynamically at runtime, the actual decision-making process of when to switch is made from static tuning. So we varied the different thresholds until we found an optimal value and created a table in our implementation. Okay.
So I see one more question here. So any suggestion for MPI improvement, generally speaking?
I think the implementations such as NVPitch GDR, they are fairly performant, but for open source implementations such as OpenMPI, I think improvement in terms of GPU acceleration would be great, because right now they just copy the data to the host and use their existing implementation. I understand that's done for portability reasons, but that would be something nice to see.
Okay. I don't see any other questions coming up in the channel. I recommend everyone to please use the channel, the Slack channel for this paper to post further questions for Yelton. And I recommend you, Yelton, have a look at the questions in future to answer them.
Thank you.
So if that's all for this session, thank you everyone for listening.